Okay, so what we are trying to do is we are trying to solve Ax is equal to B, and A is a square matrix, and that's the particular case that we are currently looking at. Obviously, B is a vector in Rn. We want to find X such that Ax is equal to B. Right? That's the problem we are trying to solve, and we are through with the existence of solution. We are through with how to compute these solutions using QR decomposition or LU decomposition, Gaussian elimination, these type of things. And we are looking at sensitivity analysis, right? So sensitivity analysis actually says that if you have B plus delta B instead of B, that's what we are looking at, then the solution X will get perturbed to A, X plus delta is equal to B plus delta B. Okay, so what we are doing, allowing perturbations in B only. Okay, allowing perturbations in B only. So I will state a result later on where we'll allow perturbations in A as well, right? So both A and B will be allowed to perturb. That is the most natural case that we will see in real life applications. And we want to see how the solution deteriorates, right? How much is the effect on solution X, so X plus delta X. So the result I think that we proved was this norm of delta X by X is less than or equal to norm of A inverse into delta B by B. Right? So relative error in B bounds relative error in X above with a scaling factor, right? And the scaling factor that we had here is called as condition number of this matrix A. Okay, so this number is called as condition number of the matrix A. And we are trying to understand the geometrical meaning of this condition number, right? So what we are looking at is geometrical. Okay, just a minute. Okay, sorry. Today my daughter wants to play in the same room where I am teaching. So, so geometrically, what is really happening? Okay, so that's what we really are interested to see. Geometrically, what is happening? So we saw what is the geometrical interpretation of condition number. We are going to see today. Okay, so geometrically, what does condition number of A means? So we looked at this particular thing, action of A, right? So we tried to understand this action of A. So this is a unit circle, and you act A, and we defined two things. We first saw that this transfers into this ellipse type of thing, right? So this unit ball transfers into ellipse. Geometrically, that is what is happening. And we defined the two things related to this. So we defined what is maximum magnification of A, and this maximum magnification of A was maximum of this norm of Ax, right? So that is the maximum stretching that you will see in any vector x after action of A. And similarly, we define something which is called as minimum magnification of A, which is nothing but minimum of this, right? So magnification is minimum of 2 norm of Ax, right? So this is minimum magnification of A. So maximum magnification, we saw it is along the major axis. So this is the maximum magnification, and along the minor axis you saw you get the minimum magnification, right? So circle is going to ellipse, ellipse is really getting elongated, and this is what is happening, right? So we also saw last time that certain matrices A, for example, rotators, for example, right? Rotators had this property, maximum magnification of Q was equal to 1, minimum magnification of Q also was equal to 1. In fact, not only rotators, all the orthogonal matrices, right? So we have seen orthogonal matrices. The property of orthogonal matrices being maximum and minimum magnifications, they are same one. What does that mean? That means that actually circle is going to circle, right? So not only that circle is going to circle, unit circle is going to unit circle. There is no change in the length of the vectors also. It's not that bigger circle is going to a circle with smaller radius and vice versa. Unit circle is going to unit circle. Best possible thing that you can think of, right? So orthogonal matrices have this property, but every matrix does not have that property. So we tried to draw some circle and ellipse using an example. I remember I made a mistake. I drew ellipse which should have been major axis along x-axis rather than y-axis. I think this is the example that we were talking of, right? Yeah. So this was the numerical example that we were seeing, and we were understanding how these how this parameter alpha actually decides what is really going to happen, right? So this is something that we already saw in last class. Okay, so we want to take this one step further, and we really want to understand what this condition number now, how can we relate to condition number to this maximum magnification and minimum magnification. Okay, so the result that we are really going to prove, condition number of A is basically maximum magnification of A divided by minimum magnification of A. Okay, so that's the result that we are trying to. So if you see, you are having a circle. Under the action of A, the circle is transforming into an ellipse. Okay, so the half length of major axis is major magnification, half length of minor axis is minimum magnification, and you are basically looking at the ratio of maximum magnification to the minimum magnification. So what you are really looking at is that when you act A on the unit circle, how much the shape of circle changes. So in this particular case, when a circle is going to circle, maximum to minimum magnification ratio is 1, right? There is no major minor axis, there is only diameter to the circle, and you will get this equal to 1. So the condition number best possible value is 1. We understand through this ratio also that the best possible value for condition number is 1. But as you start increasing this condition number, as the maximum magnification becomes larger and larger compared to the minimum magnification, this ratio starts to increase. Then what do you observe? As this ratio starts to increase, the ellipse really starts becoming, like ellipse which looks like this. And after some time, if the ratio still increases, the ellipse starts to look like a degenerate ellipse, right? So in the worst case possible, the ellipse will fall down onto a line segment, right, in this particular example. But here, because we are assuming that the matrix is invertible, then minimum magnification cannot be 0, right? Because if the minimum magnification is 0, what does that mean? That means that there exists a vector x such that ax is equal to 0, right? If ax is equal to 0 for a non-zero x, in fact x has norm 1, what you are saying, the columns of A are linearly dependent. Columns of A are linearly dependent means that the matrix is not invertible. So what we are really saying is that minimum magnification has to be non-zero, but if it is really small compared to the maximum magnification, then the ellipse that you see is really very bad. And that bad shaped ellipse corresponds to high condition number. As the ellipse tends to go to circle, condition number starts decreasing. Eventually that ellipse will fall down onto a unit circle. Then that is the best possible case. That is the orthogonal matrices. Okay, so that is something that is really very important. So we know by definition, this is something that we want to prove. Okay, so when you see a matrix which is ill conditioned, that means that the condition number is really very high. Immediately what should click in your mind is that there is a unit circle, and that unit circle is going to an ellipse which is really very bad ellipse, right? Bad in the sense that major axis is really big than the minor axis, right? So that is how that ellipse really looks, and that is what is happening to the unit circle, and that's what the condition number being very high really is meaning. When you see orthogonal matrices, your mental image should be that a unit circle is going to unit circle. And now this analogy you can draw further. You can go to a three-dimensional case, you go to an n-dimensional case, then you will have a unit sphere, and that unit sphere distorts into an ellipsoid. You have a major axis for the ellipsoid and you have minor axis for the ellipsoid. In between there are certain axes again. Those axes will be very important to us. We will try to relate them with SVD. But right now you just think of major axis, the highest length in that ellipsoid, and the minor axis, the smallest length in that ellipsoid. And you look at those ratios and the ratio becomes really big, ellipsoid starts to become flatter, right? So it starts to become flatter. So if that is happening, then condition number is really very high. That's the geometrical interpretation. But in order to get that geometrical interpretation, we first need to prove this result, that condition number of A is really maximum magnification of A divided by minimum magnification of A. The condition of the definition of condition number that we know is this: A into A inverse. That is the definition of condition number we know, right? So we know this definition and we want to get to this definition. Okay, so in order to get to this definition, we'll prove couple of results. Okay, so those results are really interesting. So let us prove those results. Okay, so they give really nice idea. So minimum magnification of A is actually 1 upon minimum magnification of A inverse, and maximum magnification of A inverse is actually 1 upon minimum magnification of A. Okay, so these are the two results that we really want to prove, and once we prove these results, then our job is done, right? We can prove this interpretation of condition number as maximum magnification and minimum magnification ratio. So A is non-singular matrix, right? So A is invertible matrix. Then this happens. Okay, the result says that this happens. So how do we prove this? The proof is not really very difficult. So A is non-singular. A is non-singular, meaning A is invertible. Okay, non-singular and invertible, same words. So if A is invertible, that means that Ax is equal to 0 implies and implied by x is equal to 0. Okay. So there is only one vector in the null space of A, which is the 0 vector. No other vector is in the null space of A, because the same argument that I just said. If there is a non-zero vector in null space, that means that columns of A are linearly dependent. That cannot happen, right? So invertibility means full column rank. We had seen that. So Ax is equal to 0 if and only if x is equal to 0. Also, A is invertible implies A is 1 to 1 also, right? 1 to 1. And you can actually talk of inverse map. That means that if you have Ax is equal to y, that means that you can write A is equal to x is equal to A inverse y, right? So you can do that. That is allowed because A is 1 to 1. So these are the two things that are important. We'll use these things, and using these things we'll write them. Okay. So what is the maximum magnification of A by definition? Maximum magnification of A by definition is maximum of x not equal to 0 norm of Ax by norm of x, right? So that is the definition of maximum magnification of A. So what I will do is I will write down maximum magnification of y not equal to 0. I let Ax is equal to y, and then x will be equal to A inverse of y. Is that right? This is what I will have according to the argument that I have here. Because x is not equal to 0, y also is not equal to 0. It is coming out because of non-singularity here. So these two things I am using to write it down in this particular format, right? So I can write it down in this particular way. And once I write it down in this particular way, if I take the inverse of this, then do you agree that I will get maximum will get converted to minimum norm of A inverse y. I am looking at 1 by, right? So if I am maximizing x, then I am minimizing 1 by x. That's the idea I am using, and that will give me what I really wanted. 1 upon, so this will be 1 upon minimum magnification of A inverse, correct? So this will be 1 upon minimum magnification of A inverse. So maximum magnification of A, you can see is same as 1 upon minimum magnification of A inverse. And if I replace A by A inverse, then I get this second result, right? Maximum magnification of A inverse will be equal to 1 upon minimum magnification of A. I replace this A by A inverse, I get that result. So basically I can write down maximum magnification of A and minimum magnification of A inverse. There is a relation. This is the relation that you really see here. Okay. So once you have this access, once you have this particular relationship, then now you see condition number of A. What is condition number of A? Condition number of A is 2 norm of A into 2 norm of A inverse, which is nothing but maximum magnification of A times maximum magnification of A inverse, because 2 norm is basically maximum magnification, and maximum magnification of A. And now what is maximum magnification of A inverse? Maximum magnification of A inverse according to this result is actually minimum magnification of A. So I'll replace it with minimum magnification of A, right? So this little small algebra actually tells me that condition number is actually the ratio of this major axis to minor axis, right? So that is what geometrically condition number is telling you. So this is what condition number is really doing. And this understanding, this interpretation of condition number is really very important, because this is something that we will have to encounter in singular value decomposition. This is something that we will encounter in principal component analysis also, because these things are really very well connected. SVD and PCA, they are not really different. They're actually the same thing. So if you understand this geometrically, then we are going to speak of SVD. You will not have any trouble. So if there is anything that you want to discuss here, we can discuss here. Please feel free to ask questions at this point. Okay, so now I had asked you a question a while back. A while back, I had asked you a question. So the question was, you have Ax is equal to B. You have Ax is equal to B, and you have Ax plus delta x is equal to B plus delta B, right? Okay, now you know that if condition number of A is very large. Okay, condition number of A is very large. Such a matrix we'll call ill-conditioned matrix. Okay. Conditioned matrix. And you see, I had asked you, if this delta B by B is small, because condition number of A is large, delta x by x, this relative error in x, may be small, may be large. Correct? It is not necessary that every time delta x by x has to be small. The worst part is you can always find out a delta B such that you will have this delta x by x to be really very large if condition number of A is large. But every time it is not necessary. I think in the example also we had seen that there was one perturbation which was okay. There was another perturbation which was not okay. So the question that I was asking is that which is the direction delta B which will have a small perturbation that will induce a very large perturbation delta x in x. So can you tell what that would be? What is that delta B? Can you answer that question? First of all, do you understand the question I'm asking? I'm not sure if I'm making myself clear. So do you understand this question?
Sir, can you explain it once again? What was the question here?
So the question I'm trying to ask here is the following. Okay, so you understand this sensitivity analysis thing. So I am perturbing B to delta B plus delta B. Okay, I am perturbing B to delta B. Then X will get perturbed to X plus delta X. I am already telling you that condition number of A is really very large. Okay, so A is an ill-conditioned matrix. So there is a chance that a small perturbation delta B may induce a very large perturbation delta X, right? So I think it is better if we can find out that example. I don't know. Yeah. Great. This example. So you see in this particular example, we had three cases. You see delta B was perturbed very slightly, right? Delta B was perturbed very slightly. It went to 0.01, 0.01, right? That was the perturbation in delta B. Then what was X? In one case, X plus delta X was very small, and in other case, X plus delta X was really very large, right? So if the perturbation was in this direction, minus 0.01, 0.01, then you see Z becomes really very large. It goes away too far away from X. But if I have this perturbation which is 0.01 and 0.01, then I get the answer which is also very close by, right? The answer that I got is close by. So if you look at delta B here, so the delta B that you have here, the norm of delta B is exactly the same in both the cases. Do you see? But one direction of delta B is causing havoc. You are getting this value as your solution, but the other value of delta B is not causing too much of a problem to you. So the question I am asking is which directions of delta B are really very problematic directions of delta B? Can you tell what directions of delta B are problematic and what directions of delta B are not so problematic? This was the question I had asked some time back also. I'm asking you this question again. Can you think of what are the directions that are going to cause trouble?
Sir,
Huh?
sir, so like the max norm of A that we had defined. So now the maximum magnification of A will be achieved for a certain vector and the minimum magnification of A will be achieved for a certain vector.
Correct.
So let's say B is lying somewhere and I perturb B.
Hmm.
And let's say there are two other vectors, A min and A max, such that for A max we see the maximum magnification of A and for A min we see the minimum magnification of A. Now, if the perturbation of B is such that B moves towards A max, then the change in delta x will shoot up. And if B is perturbed such that it moves towards A min, then the perturbation will shoot down in x.
Okay, so you think about this argument once again, Kshitij. Okay, but there is a simpler argument to this. Okay, so what you just said, you try to match with what I'm trying to say. Then you will see what is happening. Okay, so all of you remember this proof that we were trying to do. How were we trying to prove this? So you had A plus AX plus A delta X is equal to B plus delta B, right? That's what we were saying. And then, so this comes from this equation, right? AX plus delta X is equal to B plus delta B. And we already know that AX is equal to B, so I cancel this AX is equal to B. So what do I get? I get A delta X is equal to delta B, right? And this means that delta X is equal to A inverse into delta B. Now, if you see this equation, from this equation, can you tell me what are the delta B's which might be troublesome and what are the delta B's that might not be troublesome? From this equation, again, Kshitij or anybody, you look at this equation and then tell me what is really delta B doing. So which direction delta B should be to inflict maximum pain on delta X, and which direction delta B should be so that it will not be that much of a trouble?
Uh, so why did we cut AX and B?
Because X is equal to B, that is known to us.
Yeah, but in this case, AX plus delta X is B plus delta B.
Yeah. So I perturb B to B plus delta B. Then I got a solution which is X hat. A X hat is equal to B plus delta B. I define X hat to be equal to X plus delta X. I can always do that, right? So delta X will be X hat minus X. So that's what I am doing. So I am writing X hat as X plus delta X. So I can always do that. So that's what I have done. And by doing it, I have obtained this. This is how we proved that result, no? Sensitivity analysis result, the result that I am showing here, this result that you are seeing, this is the way we proved this result, no? I have just written a step in the proof. That's what I have written. So where should delta B be? What is the direction of delta? So A inverse has a direction of maximum magnification. A inverse has a direction of minimum magnification, right? So you have this scenario, you have a unit circle here. That unit circle is really going to be a very bad ellipse, right? So this is something that we already know because condition number of A is bad. If I say condition number of A is bad, do you all agree that condition number of A inverse is also bad?
Yes, sir.
What is condition number of A inverse in fact?
Same as condition number of A.
Same as condition number of A. So whatever is the condition number of A inverse, condition number of A and A inverse, they are all same, right? So suppose I look at this mapping A inverse, then there is a direction here, and this direction, say for example, this direction actually goes in the direction of maximum magnification, correct? So A inverse, when you apply on this particular direction, you really get a large magnification. So in this particular equation that you see, if delta B happens to be in the direction, so if delta B happens to be in the direction of maximum magnification of A inverse, then A inverse delta B will be really magnified out of proportion. And that magnification that A inverse causes to delta B is actually reflected in delta X. And that delta X you are actually adding to X, right? In order to get the perturb solution, you are adding that delta X to X. So that is the direction of the perturbation of delta B. So the direction in which delta B has this perturbation where maximum magnification is going to occur. If delta B is given in that direction, then you have a very bad effect on X. But if delta B is given in a direction where A inverse does not take drastic action on delta B, magnification in the minimum magnification direction, then delta X norm is also going to be small. If the delta X norm is also going to be small, then possibly this X plus delta X is going to be small, right? So this is something that you have to understand. And I want you to spend some time on this. And understand what is really happening here. Okay, so this particular question that I am writing here, I'm going to put this question either in your next assignment or I'm going to ask this question in your exam. Okay, so I am already telling you this. Next exam, I'll either ask this question or I will ask this question in the assignment. I want you all to make sure that you understand this. What is really happening? Every time it is not necessary that delta B will induce X plus delta X, which is really far away from X. Even if matrix is ill conditioned, it is not necessary. But if the matrix is ill conditioned, then you can always find out one delta B for which this will be really very large. But not every delta B will cause this to be really very large. Okay, so that is something that I'm trying to emphasize. I'm not sure if I'm doing it very convincingly, but you look at this particular diagram, you look at this particular thing, you look at this particular expression, and from this expression try to figure out what is the direction delta B that you will give, so that X plus delta X will be really too far away from X. Okay, so that is something I want you to think about. Okay, so this is very important. If you understand this part, then I think the whole sensitivity analysis that we are trying to look at will be clear. Okay, so this is one aspect. This is one aspect of condition number. Okay, so another interpretation of ill-conditioned matrices. Okay, another interpretation of ill-conditioned matrices. So this interpretation of ill-conditioned matrices is something that is really very helpful, and this interpretation will come very useful when you are doing regression or you are doing principal component analysis. This interpretation helps a lot. Okay, so that is something that we want to understand. So let us look at this interpretation carefully. Okay, so let A be a matrix which is in Rn cross n. Okay, let A be a matrix which is in Rn cross n, and let A be not invertible. Okay, let A be not invertible. So what I'm saying, A is not invertible. That means that columns of A are linearly dependent, correct? Columns of A are linearly dependent. If columns of A are linearly dependent, then there exists a vector x in Rn, x not equal to 0, such that Ax is equal to 0. Do you all agree that this is what it really means? So what I will do is, without loss of generality, okay, without loss of generality, I'll say assume that norm of x is equal to 1. Can I do that? Of course I can do that, because the direction of x is what is really important. Norm of x is not important. If norm of x is not equal to 1, then I divide the vector x by its norm. And then I still get ax divided by norm x is equal to 0. That x by norm x I call y. Ay is equal to 0, the same thing, right? So that y I am calling x. So without loss of generality, I can assume that the 2 norm of vector x is actually equal to 1. But what does that mean? That really means that minimum magnification of A is actually equal to 0. You see, x is equal to norm of x is equal to 1. What is the definition of minimum magnification? Minimum magnification of A is basically minimum over x equal to 1, norm of x. Because you are looking at norm of Ax to norm, this minimum magnification is always going to be greater than or equal to 0, because all these numbers whose minimum you are looking are all greater than equal to 0. Because A is not invertible, you have been able to produce a x with norm 1 such that Ax is equal to 0. That means that minimum magnification of A is equal to 0, right? Minimum magnification of A is equal to 0. So whenever A is invertible, A is not invertible matrix, whenever A is rank deficient matrix, it's not invertible, then you see that the minimum magnification of A is actually equal to 0, right? You see this minimum magnification of A is actually equal to 0. This is something that is really very important. This observation is important. Okay. So now you start with the other way around. Okay. Now I want to look at it from the other way around. So let A be a matrix. Let A be a matrix which is ill conditioned, right? Which is ill conditioned. So if this matrix is ill conditioned, that means that condition number of A is really bigger than 1, right? And what is this condition number of matrix? So this is maximum magnification of A divided by minimum magnification of A. Okay, and this is really bigger than. So I will apply same logic. I'll say that without loss of generality, assume that maximum magnification of A is actually equal to 2 norm of A is equal to 1. If it is not 1, then I'll divide it by its 2 norm and I will get it to be equal to 1, right? So I will assume that this is equal to 1. So if the condition number, in the condition number calculation, if you know that maximum magnification or 2 norm is really greater than 1, then what it really means from here is that condition number of A very bigger than 1. It actually implies that 1 upon minimum magnification of A is really big, correct? And that really means that minimum magnification of A is a number which is really very small, right? So very small number, almost close to 0. Because if that number is very close to 0, then 1 upon the number which is very close to 0 will be really very big number, right? So it's almost like you are dividing by 0, 1 by 0, right? So 1 by 0, so you don't really divide by 0, so you think you are dividing by this number. So this number will be a really very large number. So this number will be a condition number which is really very large. So you're not exactly dividing by 0, but you are dividing by a number which is very small, which is very close to 0. That is what it really means when you see that the matrix A is ill conditioned. Correct? So if your minimum magnification is really very small, if your minimum magnification is really very close to 0, what does that mean? Now what does that mean? That means that there exists a vector x in Rn and norm of x is equal to 1 such that Ax is very, very small. Okay, is that right? So when I'm saying Ax is very, very small, what I really mean is that Ax is almost 0. Ax is almost 0, right? So this 2 norm of the vector is almost 0. That means that vector is almost 0. So this is little bit of hand waving that I am doing, right? And that means that columns of A are almost linearly dependent, right? Because the non-trivial linear combination of columns of A is going to 0, right? Almost 0. So the columns are almost linearly dependent. That means that matrix A is almost non-invertible, or it is called as almost singular, right? So this is something that is the matrix A is almost non-invertible or matrix A is almost singular. Does that make sense? So if you have a very high condition number, if the matrix A is ill conditioned, according to this logic, what it really means? It really means that the matrix is almost a singular matrix, right? It is almost a non-invertible matrix. Why that almost is coming in? The term almost is coming in because it is very, very small, right? So the minimum magnification is really very, very small. So minimum magnification is really very small means that the columns of A are almost linearly dependent, right? Because you take that linear combination of columns and you are getting almost 0. You are getting almost 0, right? So if that is the case, then columns of A are almost linearly dependent. That means that the matrix A is almost singular matrix, right? Matrix A is almost singular matrix. So what it really means is that the matrix that you started with, the matrix A that you started with, the columns are almost linearly dependent. That means that there is a redundancy that you can have amongst the columns of A, right? The linear redundancy, of course, we are not talking of non-linearity anyway, but the columns of A are almost linearly redundant. That means that there is one column which can be written as linear combination of the remaining columns. Now think of a situation where columns of A are actually representing certain attributes, right? The rows of A are actually the data points and columns of A are actually the attributes, right? Those attributes are really very important to you. You have those attributes. So attributes, or sometimes you call them features, right? So the columns of A are features. And now if you see the matrix A is ill conditioned. Now you see that matrix A is ill conditioned. What does it really mean to say that matrix A is ill conditioned? It really means that the columns of A are almost linearly dependent. What does that mean? That means that the features have almost linear redundancy amongst them. That means that one feature can be written as linear combination of other features. So you can do away with that feature. You will not lose information, because anyway the information stored in that feature could have been recovered by the linear combination of the remaining features. Had this matrix been such that it was not invertible, had this matrix been such, the matrix A, if it were such that it was not invertible, then you know that there is exactly a column, there is exactly a feature which is linear combination of other features, exactly according to this logic. What is that linear combination? That linear combination is basically the vector x. That's the linear combination that you're talking about. But unfortunately, what happens? A will be corrupted by certain measurement noises. So you will not have exact A, but you will have perturbed A. If you have perturbed A, then the matrix will be ill conditioned, possibly not non-invertible. And then you can use this concept. And this is what you do exactly in principal component analysis. That's what you are doing. You are looking at features. Looking at the features, you are saying that, okay, one feature can be deduced from other features by certain linear combination. So you can do away with that feature. Okay, so roughly that is what you're doing when you do dimensionality reduction, right? So what is dimensionality reduction? You get away, you do away with those certain type of features. So little bit more than that you do. So we'll understand that clearly in what happens in principal component analysis. But this is something that is really very important. So almost all of you have taken regression possibly as your elective course sometime back. So in the regression course, what you have seen in the regression course, you have seen that you do this multicollinearity concept in regression, right? What is that multicollinearity concept in regression telling you? Multicollinearity concept in regression really says that one of the independent variables in regression, or regressors as you call them in regression, one of the regressor can be linearly deduced from remaining regressors, right? Then you are talking of condition ratios in that you are talking of condition ratios in regression course most probably. Those condition ratios are nothing but one of the condition ratios is actually the condition number of the matrix A. Okay, so that condition number of matrix A really decides what it decides. It really decides that can you say that the columns are almost linearly dependent? If you can say columns are almost linearly dependent, then your job is done, right? So that is where we want to stretch this concept. So we are almost there now. So that is where we are going, right? And once we understand this interpretation of condition number, this another interpretation of condition number, that opens up a whole new avenue for us to go that direction. So this will take us to the path of singular value decomposition, principal component analysis, multicollinearity problem in regression, principal component regression. These are the type of things that we will be able to look at after looking at the interpretation of condition number in this particular way. Okay, another way of interpretation of condition number is minimum magnification by maximum magnification, maximum magnification by minimum magnification. That tells us how the circles are going into ellipses, right? So if the ellipse is really very bad, then you know that there is a problem. What is the problem? The problem is the problem of sensitivity. This problem also is going to occur in real life applications when you are trying to solve least squares problem. So we'll get to the least squares problem now shortly. So far we are talking of n by n system, but in the least squares problem, B and A matrices are always going to be perturbed. So what you are always going to find out is x plus delta x. The question you are asking is that x plus delta x really close to x? That's the question we are asking. That depends on the condition number of A. What does that mean? That means that are the circles going to circles, or are the circles going to the ellipsoids, right? Really bad ellipsoids. So again, all of those who have taken regression as your elective previously, you would remember that in the regression, I think you did something like this, right? So Ax is equal to B, and suppose this x is the parameter vector, right? So I think in regression your notation was x beta is equal to y, right? Possibly, and beta is the parameters that you are trying to estimate. Then you had this expression x transpose x inverse x transpose y. So this x transpose x inverse x transpose should ring a bell now to you, because this is the left inverse that we have seen already, right? So this left inverse is going to come back. And then you were talking of distribution of this beta, right? Beta follows normal density, and in that normal density you would have seen that this x transpose x inverse really plays a role, right? So this particular matrix x transpose x inverse has something to do with the covariance of this particular parameter vector beta in the normal density, right? So that covariance is really very high or really very small. That again is governed by the condition number of this matrix X. Okay, so the condition number of this matrix. So in our notation, condition number of A really determines how much is the variation in the parameter. So if your data changes slightly, how much is the variation in parameter that you expect? So if you have very small change in data and that results in very big change in parameter vector, so every time you add a new data, possibly you are changing your parameters drastically. That is something that is not advisable, right? You don't want these parameters to vary too much, because you are going to use these parameters in subsequent analysis to make some decisions. If the parameters change too much, I think that is something that is not desirable, right? So in regression course, you would have seen that orthogonal design is something that they say is always desirable. What is orthogonal design? The orthogonal design really says that columns of X are orthogonal to each other. What does that really mean to us as linear algebra person? It really means to us that you want columns of A to be orthogonal. So what you really are saying is that the condition number of matrix A is really very good. If the condition number of matrix A is really very good, basically you are saying that you have a situation where circle is going to a circle. Right? So these are all the different types of things that are really very important. So these are the types of connections that we are going to get into now. Okay, so far you would have seen only linear algebra. So far you would have only thought that this is like probably only purely linear algebra course, but this is the point where it will start differing from a pure linear algebra course, and this is where we'll start looking into these problems from AI and ML. Okay, so this is what we really are going to look at henceforth. So is it clear what we are going to do now, how we are going to relate these concepts of linear algebra to the concepts in AI and ML? So whatever I have said just now in last 5-10 minutes, we are actually going to prove everything mathematically in the class. Okay, I'm going to give you proofs of all those things in the class. So that is what we are going to do for next 1 month mostly, and then the last after the second exam, the last month will be based on all these different decompositions and their connections with possibly deep learning or some other problems. Okay, so that is what we are roughly going to do. So is it clear what is going to come next and how you are going to put those things in context? So anything that you want to say here now, I think you're free to say it. Okay, so any other place you had seen the applications of these concepts? Yes, Ramdas, please.
Sir, how did we assume without loss of generality that the second norm of matrix A is 1?
Okay, so you just so if you have A, then you divide it by this. That's all. Then this matrix will have norm 1, right? The norm of this matrix will be. That's what I really mean. Anything?
Sir, did we already
yes.
prove that if orthogonal, the columns of A are orthogonal, then the condition of the K2 is really very good?
Yeah, we already proved it, right? Why we proved it? Because if you remember a result of orthogonal matrices, what is the result of orthogonal matrices that we had seen? So the result in orthogonal matrices was that Qx is equal to X norm for every X in Rn. Do you remember this result that we proved for orthogonal matrices?
Yes.
So if you have this result, then what is maximum magnification? Is basically Qx by X, and you will look at the maximum X not equal to 0. So that is 1. And similarly, minimum magnification is 1. So maximum by minimum magnification is 1. So condition number is 1. So for orthogonal matrices, condition number is always 1. 2 norm. Okay, we are always talking of spectral norm. I am not talking of any other norm here. So we are sticking to spectral norm. Is that fine, Ramnivas? Do you recall this?
Yes.
Sir, for
Yes.
condition number, we have this inequality that will be greater than or equal to 1. Can you just give an intuition why we can't have a matrix which scales all the elements to lesser degree? I mean, so that every vector is scaled down.
So that is very easy, no? You can see that is not a problem. So that is not a problem. So suppose you have a matrix A. Okay, suppose you have sorry. Okay. So suppose you have a matrix A which is equal to alpha 0 0 beta. Okay, alpha is positive, beta is positive, and alpha beta both of them belong to 0 to 1. Okay, strictly less than 1. Then you see maximum magnification is maximum of alpha beta, minimum magnification is minimum of alpha beta, and both of them are such that all the vectors are scaled less than 1. Do you see that?
Yeah, I see.
Is that okay, Aviraj? So based on whether alpha is greater than 0 or beta is greater than 0, your ellipse will be looking like this, right? So suppose ellipse looks like this. That really means that your alpha is greater than beta. If alpha is less than beta, then your ellipse will be on the y-axis, right? That's how the ellipse will look like. But this will always be a smaller ellipse than the unit circle, right? This length and this length, right? Always be smaller because alpha and beta are less than 1.
Yeah, got it. So
Got
even
it.
the minimum magnification can be less than 1.
Yeah, so maximum magnification can be less than 1. So you are basically having total shrinkage, but still maximum magnification will be greater than minimum magnification always, no? So
Got
the
it.
condition number will always be greater than equal to 1.
Yeah, yeah.
Anything else? Any other doubt? Yes.
We need to plot the image of the Z that we are getting, and there will be 20 images, right? So we need to put that in the PDF.
Which 20?
Like Z, suppose K equals to 20, then representative of the clusters would be like 20 images, as you said
Where is?
in the assignment question.
Oh, in the okay, in the assignment, yeah. Okay, in the assignment, yeah. So you have to represent it as an image, 28 by 28 image. Whatever representative you get, 786 vector.
There will be 20 images in total.
Yeah, you
Then
plot
need
those
to
20
put the
images now. What is big deal? You have the code ready, you have those images with you. You just have to plot them and put them in that single PDF. Do that, no problem.
in AMX algorithm, as we are doing in terms of minimum of J cluster, like we are iterating over a period of time. But can you do it in terms of number of iterations?
I am actually not able to hear you properly, Soumya. Your voice is breaking. Okay, I'll talk to you. I'll talk to you after the class. You wait after the class. I'll answer your doubts. What I really want now is that, is there any doubt related to what I have taught today? Because from tomorrow, now what I'm going to say, from tomorrow we are going to move to the next topic. So tomorrow what I'm going to do, I'm going to state only, not prove, because now the concepts are clear. If you want, you can go to the book and see. So I'm going to write down a result similar to this result, sensitivity analysis result, and that result will be basically the result where both A and B, both these matrices will be perturbed. So this result is proved only for matrix B, the vector B is perturbed, but I'll prove results similar to this sensitivity analysis. I'll just state it. I will just write down the result where both A and B are perturbed, and that's it. Okay, so we'll stop our sensitivity analysis at that point, and we'll move to the next problem, which is least squares problem. And we will get into this least squares problem. We'll understand various different types of least squares problem that we are going to do, their solutions, their relation with the left inverse, that pseudo inverse, how do we get that solution, and things like that. Once again, we'll try to understand the geometry of the least squares problem, and for some time, probably 3-4, like next week, until end of next week, we'll be talking of least squares problems, and how to solve those least squares problems, and sensitivity analysis of the least squares problems. That's what we are going to do in the following week, and tomorrow, like from tomorrow onwards, that's what I'm planning to do. Okay, so again, like that is a very important topic. Least squares problems come often in many real life applications, right? So that is what we are going to look at. So if there is no other doubt, then I think we can stop today. It's almost time. Anything anybody wants to say related to this?